Hello friends, welcome to engineering tutorial. In today's video we are going to discuss a concept which is related to the subject of control systems, which is about the block diagram reduction. Now I have already posted a video about the basic rules of block diagram reduction, the techniques that are used for simplifying a complex block diagram and to determine the transfer function of the system. There are, I think, 12 to 14 rules which are to be used to simplify a block diagram. Now I want you to please go through those two videos first and then come to this video. Here we are going to solve some questions on block diagram reduction applying those basic rules. Okay, so let's get started. So here we have been given a block diagram with input r as a function of s and output c as a function of s. Here s is the S domain, means Laplace transform is used, which is the transform method which is used in control system, the S domain. Now we have to determine the transfer function, which is output by input in S domain, using the techniques of block diagram reduction, those rules. So whenever you come across a block diagram which you have to simplify, always break the block diagram into small parts. You have to identify a point where you can apply the rules of block diagram reduction. Okay, you have to pinpoint that location and then start solving from that point, and it will automatically simplify itself one after another, one after another. The only thing is to identify from where to start. That is the most tricky part while solving a block diagram reduction question. The important thing is to identify from where to start. That is the only important thing. Okay, so let's start. So here, when we look at this block diagram, we see this summer, this summing point, this block, this summing block. It has three input points. Two are positive having plus sign, one is negative. It means it is negative feedback. So here we can apply this block diagram reduction rule, which is splitting a summing point into two parts. We can split this summer into two parts. Let us say we have a summing point like this. We have three inputs. Let's say this is A, this is B, this is C. This is positive, and this is negative. The output is A plus B minus C. Okay. Now we have to split this summer in such a way that this output remains intact. This output value we cannot change. We have to redesign it in such a way that we still get the same output, A plus B minus C. Any change in the output, it means the splitting is wrong. So we can split it in this way. See, this is A, this is B, okay, plus plus. The output is A plus B. This output, the output of this first summer, this output is given to another summer. This is positive and this is negative, this is C. So the net output is A plus B minus C. So you can see here we have split this summer into two parts. Okay, so we are going to do the same thing here. Okay, so let us do that. I am going to change it here itself. Okay, so first is this and this, and then we have another. Okay, and then we have G3, this block, and the H3 in the feedback. So we have split the summer into two parts. This is the output. Okay, so we have split the single summer into two parts. Now focus on this part. This is a negative feedback connection. Okay, a negative feedback connection. So how do we solve a negative feedback connection? Suppose we have a connection like this. G the input and output relationship is Gs by 1 plus Gs Hs, isn't it? Gs by 1 plus Gs Hs. So here also it will be G3 by 1 plus G3 H3. Okay, here it is negative feedback, that's why the plus sign here. So this entire combination will be converted into a single block with value G3 by 1 plus G3 H3. Okay, so let us convert it into one block. Okay, this gets converted into one block. Okay, okay, this much portion is solved. We can remove this part. Now here, now let us shift our focus to this part. Suppose we take this point, this takeoff point, okay, it is called as a takeoff point. If we take this point here, if we take this point and shift it behind this G2 block, it will again be converted into a negative feedback connection. Okay, so now let us understand how we take a takeoff point behind a block. See, suppose we have a block, let's say it has a value G. This is the input, this is the output. Let the input be A, the input signal be A. So the output will be of course A into G, it will be multiplied with the gain AG, the output is AG. Suppose we take a signal from here, the value will be AG, this takeoff point, this point is called as the takeoff point. So the value of this signal is AG. Now if we wish to shift this takeoff point to this point, okay, then the rule is that the value of the signal should remain unchanged. Okay, the value of the signal should remain unchanged. So if we wish to take this signal from this point to this point, we have to make some alteration, we have to make some changes so that the signal value here is also AG. Okay, so let us see how we can do that. So we are shifting this takeoff point from here to here. Okay, so the signal value here is A. Now we introduce this G block here. Okay, so here it is A, here it becomes A, G. Okay, so we introduced a G block here. When A is given to it, it gets multiplied with G and the output is AG. So we have shifted this takeoff point from here to here. So here also we wish to do the same thing. Here let's say the signal is A. So here the value, this signal value is A into G2. So if we wish to shift this takeoff point from here to here, we have to introduce a G2 block here. So let us do that. So this is the H2 block. Now we'll introduce another G2 block here. So we have shifted this takeoff point here. Now two blocks, when they are connected in cascade, the gains are multiplied. So we can again write it directly as H2 G2. Okay, we can write it as H2 G2. H2 G2, we can directly write it as H2 G2. Okay, so we have again simplified one portion of the block diagram and we have minimized it. Now it is quite easy to solve it. This portion, these two blocks are in forward path and the signals are fed to this summing block. So the gains will be added. It's just like this. It's like eliminating a forward path. Suppose we have two blocks, let's say G1 and G2 in forward path connection, the outputs of which are fed to a summer. This is positive and this is also positive. This is R, this is C. Okay. So this output C by R is G1 plus G2. This gets added. Okay, C by R is equal to G1 plus G2. So here also it will be G2 plus G4. This entire portion will be converted into a single block G2 plus G4. I have discussed in detail all these rules, basic rules of block diagram reduction in that video, so you can please check out that video first. Here also I am repeating again so that you don't get confused where I am applying which rule. Okay, so we are going to convert this entire block into a single block G2 plus G4 using this block diagram reduction rule. Okay. So this becomes G2 plus G4. Okay, this is a negative feedback connection. Okay, so as I just discussed previously, a negative feedback connection is the transfer function is given by G by 1 plus GH. Okay, GS by 1 plus GHS. So here also it will be G1 by 1 plus G1 G2 H2. Okay, so we are going to again convert this into a single block, which is G1 by 1 plus G1 G2 H2. Okay, okay. Now these three blocks, okay, G1 by 1 plus G1 G2 H2, G2 plus G4 and G3 by 1 plus G3 H3, they are connected in cascade, so they will all be multiplied. Okay, they will all be multiplied because blocks connected in cascade are multiplied together. So we can all combine this whole thing as this, as into a single block. We can combine it as like this: G1 G3 into G2 plus G4 by 1 plus G1 G2 H2 into 1 plus G3 H3, a single block, by multiplying the three individual blocks. Okay, now this is a unity negative feedback connection. This is a unity negative feedback connection. Okay, whenever we have a unity negative feedback connection, okay, it means H is 1. Okay, in case of a unity negative feedback connection, it means something like this: G In case of a unity negative feedback connection, means H is equal to 1, the transfer function is this: G by 1 plus G into 1, because H is equal to 1. The same rule is applied: G by 1 plus GH, but here H is 1, so it is G by 1 plus G. Here the forward path transfer function is this: G1 G3 by G2 plus G4 by 1 plus G1 G2 H2 by 1 plus G3 H3. Let us denote it as G. Let us denote it as G. Okay, because it will be very lengthy to write the whole expression, so let us just denote it as G. Okay, so the transfer function, the combined transfer function CS by RS will be G by this by 1 plus G into 1, and you can just solve it by cancelling the common denominators and you will get the required transfer function. Okay, so this is how you reduce a block diagram step by step, by first identifying the point where you can apply the block diagram reduction rule, and then you can automatically keep on solving each and every part until you simplify it in this single block form. Okay, so this is one of the questions. We are going to discuss some more questions related to block diagram reduction. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.